I'm just curious to get a sense of everybody here. How many of you have studied quantum mechanics? Okay, got a couple of hands, good. That's more than I expected, so that's good. And how many of you studied psychology? Okay, that's what I expected. More of that. Okay, a little bit of my background. Just recently, actually last month, published a paper of interpretation of quantum mechanics called The Lenses of Perception Interpretation of Quantum Mechanics. And one physicist called it the psychological interpretation of quantum mechanics, which is a curious name. Not something you often hear about but as we go on, you'll see more why it was nicknamed that. Also an author of a book that came out last year, Lens of Perception. It's subtitled, A Surprising New Look at the Origin of Life, the Laws of Nature, and Our Universe. So it includes subjects like neuroscience and biology and how it's all related to this subject we'll be talking about. My background worked as a Chief Technology Officer, Corporate Executive of a $1.7 billion division of GE. We did a lot of work with the Advanced Research Group that GE had there, and a co-founder of a startup on artificial intelligence, which recently sold to Motorola. So I had time to do some writing now. And inventor of over 30 patents, and I've been lecturing and writing classes on consciousness for over 40 years. Okay, so something curious has been going on for the last 100 years, and Harold Morowitz had this to say, which really captures it, I thought, fairly well. Something peculiar has been going on in science for the past 100 years. Biologists have been moving relentlessly toward the hardcore materialism that characterized 19th century physics. At the same time, physicists faced with compelling experimental evidence have been moving away from strictly mechanical models of the universe. It is as if the two disciplines were on fast-moving trains going in opposite directions and not noticing what is happening across the tracks. And although he's talking specifically about biologists here, he actually refers to psychologists later on in the quote, because really pretty similar tracks that psychology have been following at the same time. Now, what is it that caused physics to turn around? It was basically quantum mechanics. The discovery of quantum mechanics has caused a major revolution in the thinking of physicists. So what are some of the things that really affect it? And just a quick overview of some of the things that really change the way you have to look at things from a quantum physics standpoint. One is cause and effect reactions don't actually exist at the quantum level. So that's an old idea that's been learned from physics, and most people still adopt that as a way of looking at it, and it's very usable in in the large scale things. But the quantum level, you don't actually see that, largely because when it comes to the quantum particle, what it was doing before you measured it is not completely known. And so you can't actually determine the cause and effect exactly in that way. Uncertainty always exists. Nothing is completely determined. You've probably heard the Heisenberg uncertainty principle. That's part of everything you have to work with there is always involved with what's going on. Forces emerge from invisible exchanges between particles. And what this means is forces are no longer actual causes on the quantum level, they're end results. And so that changes the whole idea of what a force is. And that takes some thinking to get your mind around this. This is a big one. No outsider perception of quantum states is possible. This is typically called the measurement problem, and it's probably one of the core issues that's unresolved in quantum mechanics. What this means is that the natural coherent quantum states cannot be observed without altering them, because the act of measuring entangles the observer with the state that's being measured. Now I'm using some quantum physics terms, entanglement and quantum states. We're going to get more into that, but right now the idea is that what you're trying to measure is altered no matter how you try to measure it, you alter it in some way. So you never, how do you know what its state was like before you measured it? That's one of the big challenges with quantum mechanics. The big problem with all this is there's a great deal of formalism in how to approach quantum mechanics, and there's a great deal of mathematical approaches that are very exacting, and they give very good results on predicting the probabilities of what you will see. But when it comes down to explaining why things are like this, why do things work this way, there's really no good explanation for the measurement problem. There's a number of interpretations that try to resolve these issues, but there's no well-accepted one. Quantum theory cannot even explain what a quantum state is. You can show what it is in the formalism and how to use it, but what is it? It's not really, there's not really a good explanation for what that is. Or why quantum states become entangled in the first place. This means one particle can actually share the same quantum state with another particle. Why? Why does that happen? Most of these things are unresolved. Richard Feynman, the famous physicist, put it this way: no one understands quantum mechanics. In fact, when he has his class with first-year students going into quantum mechanics, he says, you probably came thinking, I was going to explain to you why all this stuff happens. He says, my job is to tell you, don't even try understanding, because I don't understand it, my students don't understand it. You have to learn how to use these formulas without understanding it. That's obviously disconcerting for most people, not knowing. And this is probably the biggest reason why you don't see psychologists and biologists worrying about quantum mechanics, because it doesn't really make sense, right? But the other big reason, and just as important, quantum behavior is typically seen as something that applies to the subatomic world. So what would it have anything to do with psychology? Well, the lenses of perception and interpretation I talked about suggests that quantum behavior is present wherever sentient beings form relationships with each other. And I'll show you why that ties into quantum mechanics as we go on. But what this implies is that there are some direct relationships. And the example I'm going to focus on, which I think shows it pretty clearly, is what's called the replication crisis in psychology. I'm not sure if you're all familiar with it. I published an article on this earlier, which I'll be referring to. But basically, if you look at it clearly, this is the same as what I call psychology's measurement problem. It describes the same problem. You can't observe the natural psychological states of people without altering them. That's the problem. How do you find a way to get their natural responses without interfering with them? And it turns out you have the same sort of problem there. And as I'll go along, I believe that this could shake the foundations of psychology just as it shook the foundations of physics. That's how significant this is, once you see how these things tied together. Okay, so the reproducibility crisis. One example, recently 100 experiments were from respected psychology journals were tested. Of those 100, only 36 produced results in agreement with the original reports. That's obviously pretty disappointing. But it has gone on. There's been more and more tests, and have been similar results. So it wasn't just that one test. This has been done repeatedly. This has created a rift amongst psychologists. Half say the problem is about the way the reproducibility tests are run. The other half feel as if the academic ground gave away beneath their feet, to use a quote from one of the articles that talked about this. Here's another quote from The Atlantic that was talking about this issue. Crisis or not, if we end up with a more rigorous approach to science and more confidence in what it tells us, surely that is a good thing. Notice there's a question mark there. Is it a good thing? The article is uncertain because there's dispute about this issue. The premise that I'm going to say here is actually not necessarily it's a good thing, because what this is illustrating is psychology is hitting a wall, the same wall that quantum physicists have hit. There is a limit to objective observation. You can only see so many things with objective observation. It's limited. To illustrate this, I'm going to take a textbook case from psychology. And this was by Fritz Strack, who you can see here, and his coworkers did an interesting study, I believe it was back in the 70s, showed that when a person smiles, it automatically improves their mood. In other words, unconsciously, whether they realize it or not. And the test that they took, this is challenging to how do you get results like this, because they couldn't ask people to smile. They were consciously smiling, and then it kind of voids out the results. So they had to find what was happening naturally. So they came up with an ingenious solution. They asked one group of people to hold a pen in their mouth with only their teeth. And they asked the other group to hold a pen in their mouth with only their lips, right? And one looks like they're pouting and one looks like they're smiling. And then they had a control group, of course, that wasn't holding a pen in their mouth. But the test, they had no idea why they were doing this. They were being told it was a test of doing two things at the same time. Okay, so they thought that was what it was. And then they were shown a series of cartoons. And there happened to be Far Side cartoons, which is one of my favorite. But they then measured the results of how funny they thought those cartoons were. And the results were the people that had their face in the shape of a smile thought the cartoons were funnier. The test has been actually replicated many times over the last 25 years. There's been repeated tests doing that and other variations. For example, a similar experiment showed if you take a confident stance in front of a group, you feel more confident, which is very similar in terms of what it implies, and the results were positive. So Strack himself voluntarily submitted his study to the researchers who were doing these reproducibility experiments. And it failed. The test was run by 17 scientists across 8 countries using 2,000 students. They found no evidence that an unintentional smile made any difference in the funniness of the cartoons. Now, you would think this is pretty black and white. That's pretty thorough testing. Numerous groups, quite a few students, quite a few subjects involved. But as you get into looking at what's going on, you quickly enter an area that's a lot cloudier than you expected. Strack himself objected to many of the ways they were approaching the replication experiments, even voiced his objection before they even started. But he's identified a few issues that jumped out at him. But when you first hear what he's saying, my reaction was he sounded defensive. After all, thorough testing like that looks pretty convincing. But he raised some good points. One was, should researchers have excluded the results of 600 out of the 2,000 subjects because they felt the subjects were not holding the pens correctly, or their answers diverged a little too widely outside the range? He's asking, isn't that a subjective bias you're using to exclude those? And obviously, 600 out of 2,000 is quite a large number. He also noticed that many of the students were psychology students that were the subjects. Since this was a textbook case and has been shown in many textbooks, if they knew about it, that would have clearly made them, they should have never been included, is what he's saying. But while I found those interesting, it was the next one he said that struck me because it woke up a memory of my own. He said they had put cameras in the rooms to watch the students, the subjects, who were the subjects of the experiment, and he was concerned it might make them feel more self-conscious. Now that might not seem like a big deal. It's kind of a more environmental effect, right? But actually, I was reminded of it because it played an important role in another very old psychology experiment. And you may have heard of this. In 1897, George Stratton wore a pair of lenses that inverted his vision on everything he saw, and he wore them continuously. And his theory was that his mind would learn to see upside down and would adapt his vision. And sure enough, after 5 days of wearing these, he saw everything as right side up. And then, after a week, he basically felt his inverted vision was normal. Now, in those first few days, it was a difficult test. And he goes through and describes on a daily basis. First few days, he was so traumatic for him. When he would lie down to rest, he'd actually take the lenses off, put a blindfold on, just to relieve. He felt relief of stress just taking the glasses off. His eyes were still closed, but it was very, very tense experiment, dramatic. And the results were quite astonishing, actually. It created a lot of interest in psychology, and hundreds of follow-on experiments have been run. The problem is, while many have seen the same results, others failed completely. People never adapted. They never saw things the right side up. They continuously felt things were like upside down. A good example, David Linden ran the test about 100 years after Stratton did, and he failed any results, and he had a number of teams of people that were working on it. He called it a myth. So it was just a myth about upside. This issue has been going on, so I got curious about this. Why would some succeed? Why would others not? And I did a real study on it. I found the results. In the longest test that was ever run, they had people wearing lenses, inverting lenses for 40 days. Ivan Kohler discovered that when he examined his subjects with clinical tests, it interfered with their ability to adapt. And one of the ways he tested was he gave them exercises like fencing. Now, why fencing was one of the things they picked is because you have to be able to direct your arms very accurately and move out of the way. So all your movements, but what he noticed was that as soon as he started taking them in on a daily basis to run clinical tests, their progress reverted. They lost the ability. He said, what the heck's going on? He said, quote, this was hard to understand. It took him weeks to solve the mystery. After many experiments, he finally solved the problem. The subjects were adapting instinctively to how to move, to how to fence, to how to walk around, to get used to wearing the lenses. They weren't thinking about it, it's just they were learning it unconsciously, you could say. As soon as they began thinking objectively, it broke their perceptual set. That means they reverted back to their old way of seeing, and that's when their progress reverted. They actually were having a harder time adapting. Their progress went backwards. This is exactly the same mistake Linden made. He brought everybody in on a daily basis to run a clinical test, asking them to think objectively, answer questions objectively, putting them in an objective state of mind. It was interfering with their natural and unconscious way of relating to what they're doing. It's really curious. In a sense, the objectivity was interfering. And since this was what was happening, Strack was right. Adding cameras could make them more self-conscious. They're going to be looking at the camera and thinking, somebody's looking at me. They're thinking of themselves from the outside point of view, right? That would make them see what they're doing more objectively, and that could make their actions less natural. But worse, as Strack pointed out, the subjects were put into a room Nobody else was present. There, with pre-recorded video to tell them the instructions on what they were supposed to do and how everything was supposed to happen. And the environment was much more sterile and impersonal. So, as I think you would all know, when you walk into a clinical environment, there's less smiling, there's less, it clearly has an effect on your sense of humor. Standing in a court in front of a judge, things don't seem quite as funny there. And I think it's intentional, right? So, objectivity does interfere with natural responses. And the thing you have to remember is what Strack was trying to study was the unconscious response of smiles, right? It was all unconscious. He designed his experiments to avoid the interference of conscious smile. That's why he went to such great length to find a way of putting their mouth into a smile without them realizing what they were doing. Therefore, the subjects need to feel at ease and natural, or it was going to suppress the results. And that's exactly what those replication experiments were doing. Thinking critically and objectively about what they were doing will interfere. Now, this is similar to what's going on in quantum mechanics. It's called the collapse of the quantum state. When you take a measurement, it collapses the quantum state. It doesn't have the quantum the traits and things that are so hard to understand after you take the measurement. Now you know a result. And we're seeing the same sort of thing here. The irony of all this is subjecting people in psychology experiments to rigorous clinical objectivity prevents the very thing psychologists are trying to study, natural responses. By using cameras, pre-recorded instructions to eliminate outside biases, introduced a new bias, objectivity, which we don't usually think about, right? Our modern world has become largely seeing through the eyes of objectivity. It's become probably our normal lens these days. A bias that is powerful enough to wipe out the effect of smiles. I believe this is the psychology's measurement problem. And my assertion is that this is not just similar to what's going on at the quantum mechanics level. It is the same exact problem. Now, to explain why it's the same exact problem, we have to get to the second half of the presentation. In this case, we're going to see what physicists can learn from psychology and biology. And to do that, we're going to take a look at some of the strangest quantum behaviors. In fact, the most notable quantum behaviors that are the most hard to understand, to get your head around. The first one here, there's no way to determine where a photon will land on a screen or what a particle will do next. Quantum mechanics can only predict statistical results. It's not just photons landing, it's any result. Now, if you look at this from the quantum mechanics standpoint, there's no interpretation that explains why this happens, why this is. It's just considered random. Somehow this happens randomly, and that randomness is accepted, but why? There's no good answer for that. This is one of the things that bothered Einstein. I mean, his famous quote is, God doesn't play dice. In other words, there needs to be some more of an explanation for why there is random behavior. But if we look at it from a biological or a psychology point of view, we'd see similar behavior with organisms. But it doesn't surprise us that they act this way because we know that they initiate actions. They can do things unexpectedly. This is why we can predict in general how people and other living creatures will act, but not exactly how any one individual will act. Okay? Now, we have a similarity. Maybe a second similarity, because we talked about the reproducibility crisis, right? But the interesting thing about this is, from a biological standpoint, we see a behavior, but we have more of an understanding for why it's happening. On the quantum mechanics side, you don't. That's the thing that's interesting here. Let's go on to another one. Quantum theory says that energy and matter must always be quantized. There's no such thing as half a photon. That means every time there's energy or matter, it's quantized, it's packets. And you can't cut those packets in half. Now, on the biological side, cells and living organisms also act as individuals. If you cut creatures in half, they will die or regenerate into individual functioning bodies once again. If you kill them, on the one hand, they stop acting as individuals. Their bodies settle into equilibrium with the environment. What happens? You no longer see them acting as individuals, right? This shows that the individuality, the qualitative individuality that they have, actually comes from their ability to act, their ability to do something. In other words, it's not the matter or energy of their body, but what they do with matter and energy. That's what distinguishes them as an individual. Once again, interesting similarity. We have an insight from the biology and psychology standpoint as to what this means and why this is happening. It's not surprising to us. But the quantum mechanics side doesn't. They only see this behavior and it makes no sense. Let's go on. This is a strange one. This is one that even many physicists often don't talk about. But at the quantum level, electrons are not always repelled by all other electrons. They are not always attracted to every proton. On the quantum level, it is hit or miss. We know, in general, that opposites attract and same charges repel. And if you have a large ball that has, let's say, billions of electrons charged on it, then it's going to repel another ball that has billions of electrons charged every time. But when you look at the quantum level, on the individual level, it's hit or miss. It's not consistent. This is similar to human relationships. You never know for sure who is going to hit it off with others. Attraction is actually a rare sort of thing, making it special. Physicists have proven that attraction and repulsion between charged particles is also rare, about 1 out of 137. It's called the fine structure constant. That's actually pretty rare. So here again we have another similarity. And these are, I'm talking about the biggest puzzles in quantum mechanics. And what's interesting is we're starting to see a pattern here. That all these similarities are suggesting similar sorts of interpretations about what's going on here. Let's go on to another one. Fundamental particles cannot exist independently of their environment any more than living creatures can. Physicists will often consider an electron as existing outside an atom as being independent. But in fact, they're not. All organisms, every biologist knows this, they need air, food, and water to live, to continue living and being an individual. They need to be interacting and exchanging with the environment. But it's startling to see this same behavior in quanta. Particles cannot live without fields. The physicist Carlo Rovelli put it this way: fields and particles are the same thing. Now, in the case of electrons, for example, every electron belongs to what's called an electron-particle field. That's actually where the electron gets its properties, like its negative charge, its mass, and that sort of thing. The spin that it has, those properties belong to the electron. By the way, I should explain that I'm giving you very brief descriptions here. If you go to the paper I talked about early on, I have much longer explanations. There's a lot more backup on this. But this is one of the ones that seems a little hard to swallow. Okay, particle is a part of the particle field. But here's the interesting thing. The weak force, the weak nuclear force, has a strange effect on electrons. They stop acting like electrons and start acting like neutrinos. Neutrinos don't have the same charge. They don't have the same mass as electrons. And so they switch from being part of the electron particle field to the neutrino particle field. So here again, we can see equality, but you know it's the same. It's like as if it's not like the particle itself has disappeared. There's a continuity between this electron and the neutrino. So it's as if the particle has switched from one field to the other. Here's another one. Entangled particles align their behavior. This is what we talk about in terms of entanglement, is the term entanglement. How do they stay aligned when they're miles apart? And there's been countless experiments running on this, showing that you can have particles that are entangled and you'd be miles apart from each other. If you measure one, the other one automatically has the same complementary state. So in the case of electrons, if you have two electrons entangled, one will have a spin that's aimed up and one will have a spin that's aimed down when you run the test. And over and over again, they can prove these results are true. But how does that electron miles away? They did this in case across islands. Now, they said one electron was measured on one island, one was measured on another. How do they know the state of the other one? And there's no time involved. There's not enough time. They've run these experiments, and there's not enough time to send a message from one to the other. This is instantaneous, or it's beyond, outside of time. And then they have run tests where you can go backwards and forward in time, so it's actually backwards and forward in time, not just space, but also time as well is breached. We see similar things with human relationships. And in fact, many physicists have pointed this out. When they want to illustrate entanglement, what do they often do? They talk about human relationships often as an example, because there are so many similarities there. We complete each other's sentences. We laugh at the same jokes with our friends. We feel our friends' pains and successes as if they were our own. We often think about our friends because the invisible connection between us tugs us inwardly, even if we're miles apart. So as if there was a connection here. Now, these things are interesting because of the similarities, right? But what if these are not just similarities? What if these are the same thing going on? Then that gives us a deeper, richer insight into what's going on the quantum level. And what the quantum physicists have learned gives us a deeper insight into what this is going on a psychological level. It makes some of these psychological states much more interesting in what they might mean. Because this is still controversial, what I'm talking about here. Here's another example. Many have probably heard about this. Particles can both act like a particle and they can be wave-like. This is something that quantum physicists have learned about. Photons can look like particles when they light up a spot on the screen. That's a particle, right? They look like waves when they create interference patterns. Organisms are actually quite similar. Their particle-like nature stands out when they act as individuals. Their wave-like nature shows up when they are involved in collective group relationships. This flower shows the work of a number of cells working together. And that's when when organisms work together, we start to see this wave-like behavior. In fact, a lot of the relationship that organisms have is a back and forth. The relationship is a back and forth, responding back and forth to each other. That is the heart of the wave-like behavior we see in organisms. Okay, the Heisenberg uncertainty principle. I talked about this earlier. One of the ways you can look at this is that the more you try to nail down exactly where a particle is and where it's moving at the same time, the more that particle seems to push back. Feynman put it this way. He says, if you try and squeeze light down into a narrow little channel, it gets so limited it spreads out when it's going out the other side. That's called diffraction, because the more you narrow down where it is, the more you don't know where it's going, you see. So that is, and there's other examples that are quite like this. But we see the same thing with biologists, in biology, with animals. They don't like being pinned down either. You corner an animal, it pushes back at some point. Because they need freedom to live. They need to be able to act and move, things like this. The only way to completely stop a creature from moving is to kill it. And it turns out, on the physics standpoint, that a particle is never completely still. It needs to be having some kind of motion, some kind of action going on. So there's a similarity here. Now this is the last of the, just quick, I'm going through these, but it's similarities between organisms and fundamental quantum particles. But particles become tangible and detectable through transactions of energy. If you're going to measure one, you have to have some kind of a transaction of energy involved. That transaction of energy comes down to emission and absorption. And that's always involved in every quantum measurement that's going on. Organisms are similar. They can only live if they continue gathering and expending energy. This means consuming, which is absorbing, food, and eliminating waste, which is emitting. So once again, we see the same sort of thing. Okay, so these, we have now a long list of similarities. They're not just a long list. The list includes every aspect of quantum mechanics that is so puzzling to physicists. And you start to say, when you see all these similarities, you have to ask the question, does this mean that quanta, individual particles, could possess some form of sentience? Is this possible? Can sentience explain all of the strange behavior that has puzzled physicists for a century? And the Lenses of Perception, Interpretation, and Quantum Mechanics, which was published by a peer-reviewed journal, as I talked about earlier, shows that this is a very real possibility, that the answers are yes. This brings us to a test. So, if this is true, then we should be able to see every aspect of quantum mechanics at the level of organisms. In other words, not just some similarities. If this is true, if we're saying this is not just similarities, that they're the same thing, then we should be able to see every aspect of quantum behavior at the level of organisms. And here we come to the most difficult challenge. It's called superposition. And this is the one that usually physicists talk about you never see beyond the subatomic level. And superpositions are about the fact that when you actually, before an electron is measured, it can be in many states at the same time, many positions, many places at the same time. And then the next time you measure it, it leaps to one place. When you measure it, it's in one place. This is called superpositions. And this illustration is one particle saying, what's wrong with you? I'm in a superposition. You know, I'm all over the place. Okay, all particles act this way. But the larger an object gets, the harder it is to see this behavior. Organisms and people don't leap around this way. So do superpositions exist at the level of organisms? Is this defeated the theory? Does this break everything? The question is, where are we as beings located in our body? Not where our body is. Remember, it's the internal agent that creates the individuality, right? So where are we as the internal agent in our body? In our body. What happens? Where are we when our heart skips a beat? Where are we when our stomach is upset? When we have to go to the bathroom? Or we're solving a math problem? Don't we leap to different parts of our body depending on where our attention goes? There is evidence to support that this is actually true. And this is quite interesting. Back in 1964, Roger Sperry ran some experiments on people who had had the nerves between the left part of the brain and the right part of the brain separated. It was done because they had epilepsy issues, and it actually resolved those issues. But they wondered if the left part of the brain is receiving information independently of the right part of the brain, is it going to create a problem? Is the person going to feel like two people, not one? And he found no. They felt, acted, and their family and friends all still saw them as one person. But when they ran tests, they found that when they showed the left eye, which registered with the right brain, a word that only the left eye could see, in this case key, and the right eye saw case, and they had a division between, so the left eye and right eye could only see their portion of it. The person did not see key case. One side of the brain saw key, one side of the brain saw case. They could ask a person they could put out a key in a case and say, reach for what you see. And if their right hand is reaching, the right hand is connected to the left hand, so it reaches for the case. If their left hand reaches, it sees the key, and it reaches for the key. So in fact, the brains are processing the information separately. But, so the case, you say, so which side of the brain is the person on? Well, it means that they're actually switching. They switch according to the moment, according to the need. And you think, this is weird. Now this is getting really weird, right? But it turns out we do this all the time. We all do this. And this is the testing he went on to find out, was we all do this all the time. And in fact, if you're in a room and you're having a conversation with somebody and something else is going on in the other room, it might capture your attention for a while, but then you're back, right? Your attention shifts and it's back. When your attention's here, you ignore it. And that's exactly what we do. The stuff that's coming through one half of our brain, what's going on, we fall into the background. We ignore that stuff when it's not really primary to what's going on. Okay, so that is really, there's really quite a bit of strong evidence in there. I do go into it in more detail in my paper. But some more recent tests make this even more interesting. Turns out, when we're consciously seeing through our eyes, we can only see through one eye at a time. You don't actually see through both eyes. Now, what's going on in the brain is the left brain and the right brain are both processing data from both eyes at the same time. There's parallel processing. There's your idea of two parallel computers processing data at the same time, but not when it's conscious. When you're conscious of it, it's actually registering in your conscious mind, it's one or the other. And there's a competition of which is it going to make to your eye. And obviously it has a lot to do with your attention, what catches your attention, or what you're putting your attention on. And it turns out that the way it goes from being potentially both, like in other words, you have a 3D vision. Where does that 3D vision? It actually comes from back and forth, left, right, and then it puts that together. But which eye are you going to look at? It's the exact same issue that the quantum physicists have to decide whether a particle is going to take this path down a two-slit experiment or that path. You don't know until it becomes measured, or in this case, until it becomes conscious. So the conscious recognition of it, and Dehane, this is in his recent book, talks about this. You can now accurately determine that this conscious recognition has this same effect. There's a competition and a choice. So we have here, and I give a lot more information in my paper about this and other experiments that show, yes, we have confirmation. We are not in one place in our body. We do jump from one place to another as our attention moves. So this is what I would call an informal test, right? It's not a formal test, but we have put together here is that for everything we can see, all the quantum effects show up at the level of organisms, including, and I have in my paper, I have a long discussion on what we call the wave collapse. There's a long discussion on it. It's a really good illustration because physicists have actually talked about that happening at the human level. Some physicists have proposed it happens at the human level. So there's really good, strong evidence of that. But there's nothing in quantum theory that says it should happen at the quantum level. So the lens of perception interpretation predicts that quantum behavior should exist wherever living organisms form relationships with each other. If quantumness at the quantum level is caused by sentience, We must see the same exact behavior at every level where life forms relate to each other. This means that the lens of perception interpretation can be proved wrong by showing even one principle of true quantum behavior that does not work at the level of organisms. I have not been able to find that. But this is still an open thing, because there needs to be a lot more examination of these things. As startling as all this is, it appears to be true at the level of living organisms. That gives us a dramatically new insight into what is happening at the quantum level, significantly new insight. It now makes some sense why particles suddenly are randomly doing this or randomly doing it. It gives us a sense of it. And at the same time, at the psychology level, it gives us a sense of why we would have this reproducibility problem. Some conclusions from all this. If this is true, all unconscious behavior in organisms are quantum behaviors. The moment they become conscious, all superposition possibilities collapse down to one actuality. This is why the quantum measurement problem is the same problem behind psychology's reproducibility crisis. More importantly, the laws of physics, all this means, if it's true, implies that the laws of physics are not fundamentally mathematical laws. Somehow those mathematical laws make the world follow those laws. Nobody knows how that happens. It means fundamentally there are psychological laws, the way particles relate and interact with each other. Fields of psychology, biology, and all the social sciences would also be affected significantly by quantum effects. So the question is, why would psychology not ever be able to become the hard and fast science like old physics? Because there's too many quantum effects. In fact, there's huge numbers of quantum effects because you're at the level of the individual and their experiences. So anyway, that was the presentation. Hopefully it's kind of a thoughtful one to get you to think about possibilities here. There's more information on a website called lensofperception.com, and here's my contact information. Open for questions.